let me, yeah, okay, someone already did that. Thank you. And I think, do we have to do something on Zoom? I think it probably is working as well. But anyway, so it's a pleasure to be back. What I'm going to be talking about today is things I've been thinking about for a few years, but more actively, I would say, in the last 1.5 years. And actually, particularly here, again, in this book, I wanted to emphasize at least the cosmology aspect of what I'm now thinking about. And let me be honest again. So in the last 30 years, we've learned a lot about what we call holography as a way of thinking about systems that have quantum gravity from the point of view of string theory. And the idea there is that in order to have a true quantum description of gravity, dualities are a powerful tool. And in particular, in the context of ADS-CFT, we kind of feel that we have a solid ground because we know what conformal field theories are, and this gives us a very powerful way of thinking about gravity in anti-de Sitter space. But de Sitter space turned out to be a much harder problem, in part because, indeed, de Sitter is a time-dependent background. The way in which the space-time is structured introduces other questions than one has to sort of grapple with. And one of those questions, for example, is that if we are in an expanding universe, how can we describe quantum mechanics or quantum field theory in a way that's consistent with the rules of quantum mechanics? Because as soon as the universe is expanding, the whole notion of unitary evolution becomes a pretty confusing question, in part because, again, you're having more space available, and how do you describe that in a unitary way? So the reason I sort of started feeling more confident to start thinking about it is sort of more by accident, because indeed in the last, say, 6-7 years, people started studying a particular quantum system, which is the SYK model, which you may have heard about, which indeed has the promise of providing some dual perspective on low-dimensional gravity. But also in that case, most of the studies actually viewed this SYK model as a description of anti-de Sitter gravity, again, negative cosmological constant. But the main thing I'll be talking about today is actually sort of give you a little bit of the evidence that sort of became obvious, at least when I started looking at the theory, that this theory is actually more related to de Sitter gravity as opposed to anti-de Sitter gravity. And then basically the game that I'm going to be talking about is we're going to be maybe making a short wish list of things that we would want to have from a theory of de Sitter gravity. And then we're going to look at the SYK model, and we're going to use the SYK model itself as a way of starting to think about this problem. Because then we take quantum mechanics basically as a starting point, and the space-time should hopefully follow from it, which is part of the idea of holography. This is a double screen. I should probably go to a not split screen. I'm doing that. Preview? No. Does anyone know how to go from a split screen? Oh, this is not better. Maybe pretty good. Is this okay for everyone? Good. Although I think unless I have to slow my this, because this one is now in this part of my screen. Oh, maybe not. Anyway, here we go. This is de Sitter gravity. Wait, I'm still not good. I'll do preview one more time. And I go to display format. Here we go. Single page. And then let's go with this. Okay. I think this works. So anyway, so as I mentioned, the model I'll be talking about will actually be a candidate model for low-dimensional gravity. So I'll be making use of the idea of holography later on, but I will not sort of start with high-dimensional string theory. I basically want to do something, find a model that captures the basic physics of a soluble model of gravity. In this case, it's 2 + 1 dimensional de Sitter gravity, in which context we don't have any gravitons, and so this theory doesn't have any local degrees of freedom, and you can kind of solve it. Nonetheless, it has a few, again, mysteries, because again, it describes an expanding universe. If you're sitting at the center of an expanding universe, you actually have your own, you can call it the static patch, but it's your observable universe. So you have an observer horizon, and then Gibbons and Hawking famously argued that you can generalize the Bekenstein-Hawking argument for black holes and associate a potential sort of interpretation of entropy to the area of that horizon, which suggests that there should be an underlying quantum system with a certain number of states. But up to now, I don't think we really have sort of very concrete examples of how this works. Again, here I'm writing down the what's called then the static patch. It's the static metric for the Sitter space, which is a solution to that to the pure Einstein equation. And as I mentioned, basically one perspective one could take is that the perspective of a single observer. And now you can ask, for example, hey, suppose I would want to do holography in this context. How would I do that? And currently we don't have complete answers. There are various proposals, including people also in the room, where perhaps indeed one should be thinking about observables that sit in the far future, which indeed would be modeling what ADS-CFT does, because ADS-CFT has basically observables that sit on the boundary of entity Sitter space. In this case, the boundary of the Sitter space sits in the future. At the moment, I'm going to be maybe agnostic about where my holography picture is going to be. Basically, I do want to find a quantum system that has the features that I can recognize that the Sitter space has. Another notion of holography that one could try to look for is what you call worldwide holography, where the picture is that you would sit at a world line, you have a detector, and that's your only set of observations that you can do. So the observables would essentially be attached to that world line, and then the thing that one would like to be able to describe is what is a quantum system that's sufficient to describe the observations of a single observer. And let me motivate that also a little bit. So I mentioned before that Bekenstein and Hawking had this interpretation of the area of the horizon as being the entropy. And in order to sort of introduce that, again, I think even in their paper, they used the 2 + 1 dimensional de Sitter space as an important motivation. So suppose I put some matter in the Sitter space in 2 + 1 dimensions, then the metric takes the form as above. So E is the total amount of energy that I'm putting in the Sitter space. In 2 + 1 dimensions, there's no such thing actually as a black hole in the Sitter space. This thing is called Schwarzschild de Sitter, but it's just describing the Sitter space with a conical singularity at the location where the matter sits. And in 2 + 1 dimensions, matter only creates a conical deficit. And if space, suppose that I'm sitting actually at the location of the matter, then my horizon will actually shrink because of the conical deficit, and the amount by which it shrinks is instead of having 2 pi, I have 2 pi times 1 minus alpha, where alpha is what's called then the deficit angle, and it turns out that deficit angle can be re-expressed indeed, or at least that the area, of course, can be expressed, which is the length of that circle, can be expressed in terms of the deficit angle, and the formula looks like this, so that energy actually decreases the entropy. And what we learn from this is that the Sitter space is sort of the maximal entropy configuration of this system. and somehow when we start adding matter to it, entropy comes down. So, and there's also a temperature associated with this. There's a slight mystery. There's a funny minus sign. Normally, if you have entropy and you differentiate with respect to temperature, that's the best respect to energy, you get 1 over the temperature. In this case, I have to differentiate with respect to minus the energy in order to get the thing that we call the de Sitter temperature. Now, again, one can try to use the gravity as a way of constructing a quantum system, but I'm going to now make a jump. Actually, I'm going to make 2 jumps. Let's see, did I? Yeah, here I have my outline. So I talked about de Sitter gravity, 3D de Sitter gravity, and indeed I'm going to make a few jumps later, and then I'm going to try to sort of connect things again. So the 3D de Sitter gravity indeed has the features that I just mentioned. It's sort of, you can think about it as a topological theory because it doesn't have, again, any local degrees of freedom. And indeed it turns out that you can reformulate it in terms of a theory that we can actually sort of quantize a bit more freely, which is known as SL2CH assignments. I'll mention that. Whether or not these 2 theories are literally equivalent, I'm leaving that open, but nonetheless we'll see that there's a 3-dimensional set of a few 3-dimensional theories that behave as 3-dimensional gravity in the de Sitter space. But then there's going to be a duality with a 1-dimensional system, which is this SYK model, which we'll introduce in a second. This is an actual quantum mechanics system with a given Hamiltonian. And it's actually a little bit surprising that I can go from 3 dimensions to 1 dimension, because that's sort of slightly unusual holographic duality. But there's another system which is sort of sitting in between. That's a 2-dimensional system, which I'll call complex Liouville gravity. And it turns out that you can basically build sort of a triangle of dual, a triality, if you wish, between these different systems. So I'll outline that. Are there questions at this point? So this is my introduction. And then
yeah, well, so I guess 2 questions. So one is, in SYK, you normally average over some random coupling, so it's not really one theory of 1 Hamiltonian, it's some ensemble. Is that what you have in mind, or do you have in mind a specific?
Yeah, okay, good question. So I'm sort of, my attitude here is the following, is that SYK, it's a collection of possible systems, because it has random couplings. My attitude is the following, is I'm picking one of those elements of the ensemble, and all the questions that I'm going to be asking are sufficiently coarse-grained that I'm not going to see the actual macrophysical choice that I've made.
Okay.
So all the properties of the theory will look like the properties of the ensemble. So I'll be doing computations in the ensemble, but I'm imagining that I'm actually living in one of the choices of the ensemble.
Okay. And then a related question is that the double scaling has some large n limit. Do you have in mind that that limit is dual to 3D de Sitter gravity with finite sort of h bar and g Newton, or do you think rather that there's also some limit on the 3D gravity?
Right. So I'll be making a dictionary. So the g Newton here will be finite. Okay. As you anticipate, I will be taking a large n limit. And sort of the dictionary to some extent is a little bit the same one as you might have, say, in a matrix model. If I give you a random matrix, there might be all kinds of properties that eigenvalues have. Those eigenvalues, those properties are all captured by the Dyson ensemble or the Wigner ensemble. And then basically the geometry of that comes out of that matrix model is the thing that will be the gravity theory. And that's the analog of the correspondence here. This thing indeed captures the universal properties of this thing here. And this thing has more fine-grained structure that are not completely captured by that. But the equivalence is indeed becomes exact in the double scaling limit. And it's going to be a double scaling limit in the sense that n goes large, but there's going to be another number that will play the role of g Newton. Okay. So again, the equivalence of the 3D theories between gravity and the transiments, basically it makes use of an observation that was made in the late 80s, that if you take the Einstein action that I had before, the 3D Einstein action, and you do this slightly funny looking sort of redefinition of observables, or at least of variables, where you introduce a dry bind, a spin connection, and you take the plus and the minus combination of the two, and you try to construct and you construct the action that describes the Einstein action in the first order formalism. Then that action takes the form of a sum of two transimus terms. In the case of de Sitter gravity, basically A and A bar are each other's complex conjugate. And indeed, this transimus theory is naturally an SL2C transimus theory. So the A is going to be a gauge connection of SL2C, which is the isometry group of de Sitter space in 2+1 dimensions. And indeed, if you solve for the equations of motion of that theory, you can recover the constant curvature equations. You can also introduce matter defects that essentially look like Wilson lines of that particular gauge theory. So there's some dictionary, which I'm not going to work out in complete detail, that at least at the level of classical solutions or semi-classical analysis relates this transimus theory to gravity.
Is there an I missing in E plus omega, in E minus omega? Is E plus I omega?
Yeah, there might be an I there, which.
So matter corresponds to some specific Wilson lines, no? Because as
correct. No, so let me mention also the way I'm going to look at this theory is I'm not going to add quantum fields in the bulk. And indeed, one of the sort of points of view, at least that one can extract from recent studies of holography in low dimensions, is that precisely when you do this ensemble averaging of your dual theory, the universal properties of your ensemble are going to be captured actually by the quote-unquote pure gravity theory. So indeed, most of the bulk theories that I'll be talking about will be a pure gravity theory, but we can still introduce matter, but more as a probe, where basically we insert matter particles. And yeah, I guess your question was about the Wilson lines. And,
yeah.
Right. Now that dictionary is indeed still not entirely obvious. If I write down the usual matter action in terms of the dry bind, you have to work a little bit of how it actually literally looks in the gauge theory, but people have worked these things out. Okay, yeah.
Do you impose invertibility on E coming from the sum restriction on the sum of
Right.
A and A?
Yeah, so people often make a big deal out of that issue. I think that people sometimes make too big of a deal of that particular issue. Invertibility, of course, it's a bit of a funny condition on the combination of A and A bar. It turns out that, as I mentioned, most of the equivalence is actually at the level of semi-classical saddle points. But let me just make the following statement. In the end, if I look at the physical observables in this theory, the physical observables are going to be Wilson lines that go around a non-trivial cycle. Those Wilson lines will specify basically, it's a holonomy. It specifies an SL2C transformation. So basically, my classical solutions are labeled by specifying SL2C transformations that go around cycles. If I take de Sitter space, and everything looks like locally de Sitter, but I have some singularity somewhere that if I go around it, I come back to de Sitter, but up to an isometry. I'm also specifying the geometry by means of SL2C holonomies. So if I have a one-to-one map between SL2C holonomies that I can put down here, I will have the same. Then I can translate that into the corresponding geometry. So I'm not talking about this as a collection of fields. I'm talking about this as a collection of holonomies.
We have to restrict the holonomies to
Correct.
hyperbolic.
Yeah, right. But that's a trivial step. It's not a deep step. It's basically saying you just have to make sure that the things that have meaning in the gravity theory specify the holonomies of this theory as well.
Yeah, I'm perfectly fine with that as abstract way to formulate how to think about this quantum theory. Just
Correct.
the level of the pattern integral,
Right.
it's a less kind of
Yeah, so since the actual physical phase space of this theory is finite dimensional, I can make the mapping at the level of a finite dimensional Hilbert space. The power of this formalism is actually that this thing has a very explicit symplectic form, meaning I can actually compute commutators in this theory, which would have been harder to extract from the gravity. And yeah, so you have a phase space and have commutators. I can start trying to construct it. That's going to be possible. But the Chern-Simons language is natural indeed if you want to do things in terms of holograms. Another thing that the Chern-Simons theory does rather nicely is that if I would put this theory on a three-manifold with a boundary, then indeed, this is well known for ordinary Chern-Simons theories. There's an actual chiral edge theory that lives on the boundary of the Chern-Simons theory. That's a chiral conformal field theory. In the case of compact groups, this will be a Westermann-Witten theory. In the case of a gravitational theory, the thing that naturally lives on the boundary is actually a theory that's sort of a 2D gravity theory, if you wish, where the symmetry group of the boundary theory is the Virasoro algebra, basically. So you have the Virasoro algebra as a boundary symmetry. If I put this theory on a three-manifold with boundary, geometrically, if I take that gravity theory and I would want to construct the modes that live on the boundary, the Lagrangian for the modes that live on the boundary looks like a Liouville theory. And if you wish, you can think about the Liouville theory as nothing else than the geometric theory whose symmetry algebra is the Virasoro algebra. But there's something special about the Sitter gravity theory, that if I take the Chern-Simons theory that is associated with the Sitter gravity, the difference between the Sitter and anti-Sitter is actually the factor of I in front of that kappa. So the level here is imaginary. Whereas if that level had been real and A and A bar had been independent fields, then this would have been anti-de Sitter gravity. And if we then go back to the boundary theory as a factor of I in front of the Liouville action. And the factor of I in front of the Liouville action means that the corresponding central charge of the theory turns out to be of this form. That this theory and that theory have central charge C plus and C minus, and it's given by 13 plus I times this beta squared is that kappa, or at least. This is a theory with complex central charge that lives on the boundary. But very interestingly, if I add the two central charges, it adds up to 26.
Anything special happens at beta equal to 1, where C is real, D2 is 13.
13, it's a cell dual point. Interesting. Yeah. It's less obvious, by the way, in this theory that there's literally beta to 1 over beta symmetry, because it then flips that sign. It's a little bit subtle how that works. Beta equals 1 is interesting. I don't know. It's a good question. Theories with complex central charge by themselves are non-unitary.
So there is a relation between beta and k here, or?
Yeah, so
Kappa,
kappa is beta squared, or yeah, because in the end, in a moment I'll also introduce a parameter. Let me write it down actually. A parameter q, which is known in Chern-Simons theory. Typically, for an ordinary Chern-Simons theory, it would be e to the 2 pi I over the level of the Chern-Simons. That's a q parameter. Basically, it goes into the Jones polynomial associated with Chern-Simons theory. In our case, this becomes e to the minus 2 over kappa because of this extra factor of I. So this is going to be a number between 0 and 1. In the dictionary with Liouville theory, this thing is e to the I times a thing called b squared, which is that b. The b has this funny e to the I pi over 4 sitting here, so that b squared is imaginary, and this becomes an e to the minus I beta squared.
We got so there is
Sorry, no I. No I. And this is a number between 0 and 1. Okay. But to finish, sort of the other part of the story is that if I would imagine quantizing this theory, and actually just in the last 2 days there were some papers on the archive called the complex Liouville string that precisely studies this gravity theory, and it solves basically for the amplitudes. But the observation is precisely that because I can now just add the BC ghost, the usual thing you do in string theory, you gauge the Virasoro symmetry of this theory. Then you actually end up with a unitary theory. Because basically anything that looks like negative norm states because of the complex central charge gets projected out by the physical state condition. So this is the theory that you could actually quantize. Okay. So that's sort of the 3D, 2D gravity side of things. And it's still a developing field because this theory is only starting to be studied. So now let me go to the one-dimensional sort of starting point of my study.
You set states from a block, like in the usual RCFT case, and Simons. But then you said, okay, this theory per se doesn't make sense, so we gauge it on the boundary. So
oh. Okay, thank you. Thank you for the question. Okay, so here's the picture. Which, by the way, is part of also what's special about de Sitter versus other versus anti-de Sitter to some extent, is that so in anti-de Sitter I have a boundary, and then actually the metric is fixed on the boundary, and I'm fixing some kind of complex structure there, and then my edge theory will be a CFT, and the CFT lives on a space with a certain geometry. Now, a CFT is not a topological theory, so it actually knows about the metric. Although the bulk is a gravity theory, which is topological in the sense that it doesn't have a fixed metric, but the metric is fixed on the boundary. Okay. Now, here I'm arguing that basically this theory should be viewed, this two-dimensional theory, which lives on the boundary, should be viewed as a thing that actually has a dynamical metric, because I'm going to basically gauge the Virasoro symmetry. From the point of view of the Sitter space, this thing might sort of naturally live on the future slice, on the future boundary. Now, if I take the Chern-Simons theory and I look at the Hilbert space of that theory, it will give me states. The states are going to be this conformal block. The physical observables, however, are expectation values. And if I take expectation values, I should take the inner product. I should take an inner product between two wave functions. So the physical observables of the gravity theory are going to be inner products of the wave functions. And those inner products of the wave functions are given by taking this CFT and coupling it to gravity. So that's part of it.
So this CFT, I mean, the exponential of this S is the density matrix, and of which you take the trace.
Correct. Yeah. So yeah. So you produce both things, and then you have to take the trace in order to fold it back together. And you do that in a way by precisely making sure that on the boundary, A and A bar are equal. Basically, that's how you fold the contour. So the boundary is sort of a topological boundary, and it's no longer a thing that actually cares about the complex.
I don't know if, just to, this kappa is the ratio of the Hubble, square root of lambda over G Newton.
Correct. Yeah.
So kappa large means a
Thank you for that question. So indeed, I should have said that. This K, this kappa, which sits in the Chern-Simons theory, governs the, it's basically this number, which later, again, 2 million letters, but anyway, it's going to be called lambda. That lambda is something like 8 pi G Newton in units of the Sitter radius. That's, I guess, R de Sitter. Is that right? Yeah,
Over the Sitter.
Over R. So now let me talk about the one-dimensional starting point. So the one-dimensional starting point is this, oh, by the way, let me do one thing briefly. Although I doubt I will actually have time for this. I had this slide here which already was impressive in terms of the number of dualities. It turns out that there's a fourth corner to this diagram, this web of dualities. Surprisingly, the fourth corner of the web of dualities is n equals 4 supersymmetric gauge theory in 4 dimensions.
Equal 2.
Sorry?
Equal 2.
N equals 2 in 4 dimensions, and it's actually Seiberg-Witten theory, literally. So it turns out that Seiberg-Witten theory, which I'll explain at the end of my talk if you have time, has some duality with SL2C Simons, and it turns out that the correlation functions that you can compute in this theory can also be recognized as certain supersymmetric indices of the 4-dimensional theory. And that seems like a thing out of the blue, but surprisingly, actually, that connection with the 4D gauge theory turns out to be the most useful computational method for computing the.
Will be related to AGT concept?
Correct. So indeed, it's sort of a topological version of AGT that lands on this.
So this index is like an Nekrasov partition function for a topological theory.
Correct. But unlike the Nekrasov partition function, it's a little bit like the answer that I just gave. Turns out that the index that you compute does not depend on the parameters of the gauge theory. That would have been the analog of depending on the complex structure of the boundary. So you actually get a function that only depends on Q and certain quantum numbers. And those things match. But anyway, so SYK, as we were just discussing, it's a quantum mechanical system. It has n Majorana fermions, so n large. It has random couplings J. And we can make the couplings indeed fixed, or we can indeed do the disorder averaging, which in the computations people typically do. So these are Gaussian random couplings with an appropriately normalized variance. The Marianas, they basically couple between each other through this p-th order interaction, and p is the other number that we're taking large, but in a way where the ratio p squared over n is kept fixed. So here introduce this number lambda, and in the SYK setting, this lambda is going to be the ratio of p squared over n. And it turns out that that's the dictionary. One way of already seeing that this is the dictionary is to do a trick that people already developed in the early 2000s, which is called dynamical mean field theory, where basically you try to take that Hamiltonian, you write down its thermal partition function, you do the disorder averaging, and then you try to write down a mean field theory, or the dynamical mean field theory, just for the 2-point function. So this is the large n 2-point function averaged over all pi. And it turns out that you can rewrite the partition function of the SYK model as a functional integral of just this variable g, and actually another variable which is a Lagrange multiplier that implements this constraint. And that's called the G sigma theory. It turns out that if you now take this double scaling limit, where you take n large and you keep p large and you take this thing finite, it turns out that in that limit, that G sigma theory can be rewritten by writing basically g as some exponent of a little g, with some prefactor, maybe lambda in it. But then in terms of that little g, that G sigma theory looks like this. Which again is essentially our complex Chern-Simons theory. Why is it a complex Chern-Simons theory? It turns out that the action has a real pre-coefficient, which is n over 2ap squared. But it's an action, it's a bilocal action in terms of these variables t1 and t2. So this action is actually on a 2-dimensional spacetime with Minkowski signature, 1-1 signature. So this is a theory that looks as if it wants to be Euclidean because it doesn't have an I in front of it in the exponent, but it actually is in Minkowski space. So this is actually a Liouville theory, indeed, with an imaginary couple.
Herman, can I ask, so I'm a little confused about one thing here. So this lambda is essentially 1 over the entropy of the de Sitter.
Correct.
And so if you didn't send p to infinity and you just send n to infinity, then the entropy would go to infinity, which is what you would expect.
Correct.
But if you also send p to infinity, so that lambda is finite,
Right.
then you have a finite entropy on the,
Right.
but on the other hand, the SYK spectrum is continuous in that limit, isn't it? The double scale.
Yeah, I'll talk about spectrum in a second. But the discrepancy that you bring up, so you anticipate correctly that the entropy that's going to be associated with the de Sitter space will be basically 1 over lambda, which we'll see. And there's indeed a notion of entropy in the SYK model that will go like 1 over lambda. That's the actual entropy that we're going to see in the double scaling limit. But there's another notion of entropy which is basically just n log 2 of basically the total size of the Hilbert space.
Yeah.
Let's talk about that thing later. But indeed there's a discrepancy between 1 over lambda and something of order n.
Good. Just to see if I understand. 1 over lambda will be the limit for a small lambda of a single central charge, the central charge of only one copy, right?
Yeah, so when we talk about copies, good question. So indeed, if we want to think about sort of what it means to be focusing, so in a moment I'll actually introduce operators that survive the double scaling limit. And the operators that survive the double scaling limit are going to be a subset of the algebra of operators that I could construct in the full theory of finite n. And the theory that survives in the double scaling limit naturally has an entropy that goes like 1 over lambda. And it turns out that 1 over lambda is also the natural entropy associated with the static patch. But I want to postpone the discussion of the full entropy of the SYK model later. And I think, by the way, these are precisely the very interesting questions that you would hope to be able to learn things about in the context of the de Sitter space as well. Because actually, I will argue that in the de Sitter space you have probably similar issues. Okay, so I'm going to, basically one can solve this theory, turns out, essentially by just doing perturbation theory. You just, this is a free action, and I can just expand this exponent and start summing. Basically sum over some diagrams. These are called chord diagrams. But let me motivate those chord diagrams briefly, also just from the point of view of the SYK Hamiltonian itself. And it turns out that in the double scaling limit, again, one can exactly solve this theory. One can compute the spectrum, essentially by doing a combinatorial analysis. And the combinatorial analysis, let me go back. Here we go. These are the chord roots. So what I'm doing, I'm taking the SYK Hamiltonian, and I'm just going to compute moments of the SYK Hamiltonian by taking the trace of the Hamiltonian to the power n. And then I just have to do Wick contractions between the various fermions. Now let this be one of my Hamiltonians. Because the j is a random variable and I'm doing a Gaussian integral over j, I'm also actually doing a Wick contraction in the j indices. And the leading order contribution is such that the Wick contractions for the fermions has to align with the Wick contraction for the j indices. So the Hamiltonians basically, they find another Hamiltonian which actually has the same sort of coupling. There's a Wick contraction here, has the same fermions here, and I'm doing that Wick contraction. So this is how I'm summing chords. These are called chords, and they're basically bunches of Wick contractions where there are p lines over here. As you can now see, actually, the ratio of p squared over n keeping that finite has an interesting interpretation, because it now means that if I take two of those Wick contractions and I look at the intersection, then the probability of finding two fermions that have the same label is going to be finite, because the p squared intersections here have n fermions. So if I basically have a finite probability of having overlapping index. And that overlapping index leads to an extra minus sign in that diagram. Now if I start summing over all those minus signs, if you do the combinatorics, it turns out that it basically is a Poisson distribution and it leads to this exponent. So the chord rule is very simple, basically that if at any time that two chords intersect, I get a factor of Q. I should have called Q, I guess, the thing with two. So that's the chord rule. So basically you sum over weight contraction over lines, and every time two lines intersect, you get a factor of Q. Turns out that this combinatorial problem actually is enough to compute the spectrum of the theory. And the way this works is as follows. Is that what you're going to do is you're basically going to draw the chords. Here I draw them a little bit sort of in a rather square way. I act with the Hamiltonian several times, and I draw all these weight contractions, or at least these chords. And suppose that at a given moment in time, I'm introducing a new Hamiltonian. Okay? Then what this Hamiltonian can do, it can either sort of annihilate or weight contract with an existing chord, or indeed, like this one here, it can create a new chord. And the rules are actually such that a new chord always gets created at the lowest rung, whereas the old chord can get annihilated at any location. Those are consistent rules. And if you do that, then basically if n labels the number of chords, then h either adds a new chord, or it annihilates the one, but it annihilates one indeed where I have to introduce factors of q for each intersection. And that leads to this particular recursion relation. If I act h on a thing with n chords. Of course, there's a deep step that I took here. Basically, I assumed that there was some state associated with the thing with n chords. But this is the way people solve this thing. And this geometric series that you get here has that particular expression, and this is called the Q integer.
So here n is the number of chords. Each chord has two n's, so you always have an even number of operators that are getting this.
Right. Because you have to doing the weight contractions.
The odd ones vanish.
The odd ones vanish, so because you don't have the weight contraction. Now it turns out that this thing actually looks like what's called a Q-deformed harmonic oscillator. So because if I define A dagger this way and I define A that way, then it turns out that these things satisfy an algebra that A dagger minus Q times A dagger A is equal to 1. And at this point, although actually the expressions we're going to find look rather unusual, but if you put your introductory quantum mechanics hat on with a Q in front of it, and you ask what is the spectrum of this Hamiltonian, you actually would know the answer to some extent. Although there's a slight funny twist, it's a Q-deformed harmonic oscillator, but the Hamiltonian is not A dagger A, the Hamiltonian is A dagger plus A. So the Hamiltonian behaves like X in the harmonic oscillator. Now, the natural spectral density for the position X of a harmonic oscillator is the ground state of the harmonic oscillator, which is a Gaussian. So that's the answer. It turns out that the spectral density, indeed, of the SYK model is the Gaussian of the analog of the ground state of this Q-deformed harmonic oscillator. Because of the Q deformation, it turns out that the thing is not a Gaussian, it's a periodic Gaussian. There's a natural periodicity in the system. It turns out that h is actually naturally the cosine of an angle rather than just a real number. And then indeed the ground state is a theta function, which is also known as a periodic Gaussian. So here's the spectral density. As I said, the Hamiltonian is naturally the cosine of an angle, and the spectral density is that theta function. And if you plot it, it basically looks like this. So that's already pretty surprising, actually, if you think about it. So this is the spectrum of the double-scaled SYK model. There's a rho 0 in front of the theta function. That rho 0 is actually e to the power s naught, and s naught is of order n. But this theta function has if I write it as an exponential of an entropy, then the entropy of the maximum entropy state is of order 1 over lambda. But it has a bounded square. And the reason why this is sort of significant, and actually I'm sort of half obsessed actually with actually understanding really where this is coming from. Because this formula looks very different than a formula you would get for a CFT, for a conformal field theory. So in all the systems that we've been studying in the context of holography, the entropy of a CFT grows with the entropy at all times, with the energy at all times, and it's unbounded. So the energy spectrum can become arbitrarily high in a CFT, and the entropy keeps growing. That's known as the party formula. In this case, I have a system, and actually most physical systems are actually like this, where at some point there's a highest energy that I can reach, and indeed there's a maximum entropy point. So the Sitter space should actually also have this property. It's not possible to put an arbitrary amount of energy in the Sitter space. Things go up and things go down, meaning there is actually a maximal entropy point in the Sitter space. And so the idea is that this would be pure de Sitter space, and if I now start putting energy into the system, I'm going to lower the entropy. I'm also going to change that value theta of the angle theta. So right now I already have a couple of ingredients that start to hint at this would be de Sitter gravity. I have a maximum entropy state. I have basically this Q parameter in the game that also is there in gravity, and I have this idea that I can parameterize energies by an angle theta.
And maybe I can ask my question again, or you can tell me to wait again. But I mean, this is a density, right? It's not. There's not a maximum entropy state. There's a peak of this density.
There's a peak of the density. That's right.
So the entropy is infinite for this spectrum because it's continuous. So how can you say that it's what we want?
Yeah, so I used to have the same problem myself, but the thing is, as soon as I take a statistical approach in an ensemble, I'm going to get an entropy density. I'm going to get an entropy density. If I take one element of my ensemble, so if I pick a certain value of j.
But wouldn't you need finite n for that?
Yeah, so right. I need finite n to have that row 0 be finite.
But then how is that consistent with this identification?
No, so my philosophy is the following. I take n to be the biggest number you can think of, 10 to the 120.
Okay.
Or actually even bigger than that. Take the largest number of multiverses in one of your papers, and you multiply that times 10 to the 120. But anyway, but it's finite.
Okay.
And I take that many Majoranas, and I take some random couple. In a regime where this ratio is finite.
Some particular random couple, yeah, okay.
Then all the properties of that theory will look like this ensemble. And all the properties of the theory, at least if I want to study the universal properties, I can take this double scalar limit. With the assumption that this row 0 stays finite.
Right, but don't you want I mean, that thing in the sitter is just a number.
That's correct.
So don't you want the number you get when you compute the entropy of this, like the number of states in this theory to agree with that number in the sitter or not?
Yeah, so Lenny made this indeed the dogma of his approach to the sitter. The number that I'm going to match is indeed 1 over lambda with this. So,
okay.
And indeed 1 over lambda is the entropy that depends on theta. So that theta depends on q, and q is e to the minus lambda. So that theta function depends on lambda, and the difference in the entropy that I can pick up here as a function of energy will tell me also what the temperature is. So the de Sitter entropy is indeed all encoded in that theta function.
All right, and you're gonna
And basically what's going to happen is that there's an additive contribution to the entropy that I don't know,
okay.
but it doesn't participate in the thermodynamics of the theory. It just sits there out as a constant.
You're gonna show us this.
No, actually this formula has that structure. So if I take the logarithm of this formula, maybe I should write it down. So the S total will have an S naught, which will grow like n. plus an S1 that will depend on theta, which carries information about the energy. And this S1 goes like 1 over lambda in a way, where indeed it can start representing the situation.
All right, so you want to think of that,
This as being the thing that
that's the entropy and S2.
this is the thing that Gibbons and Hawking would start talking about.
Okay.
This one they never see,
Okay.
because it's just the constant that sits out. Okay. I'm going to, I'm probably running out of time. How am I doing with time? I have 10 minutes. Okay. Okay, I'm going to accelerate my universe. So now you're going to get the lightning review of all the other things that one can do with this theory. First I'm going to talk about the two-point function. It turns out that you can take this SYK model and you can define a two-point function in it, but you have to do it rather carefully. Turns out that basically what you have to do is you have to take 2 copies of the model, and it's sort of motivated by the structure of the Liouville theory that I had earlier, where you have 1 copy, think about it very roughly as living sort of on the North Pole, and the other copy is living on the South Pole of the SYK model, I'm sorry, of the de Sitter space, but it's slightly misleading to call it that. But anyway, what I'm doing, I'm going to be looking at a Hilbert space where I require the 2 sides to have equal energy. For those of you who studied some of the papers on the Sitter space of Pennington and Witten, they introduced something where they basically had an observer and a clock. The way I like to think about this thing is this is my clock and that's maybe my physical system. But anyway, since I have to rush, if one introduces the following definition of what I call a physical operator, where basically I'm taking a convolution of 2 SYK operators. It turns out that if you compute the two-point function of this thing, and you can do it exactly because of these Cork rules, that two-point function, again, it can be expressed in terms of theta functions. So it turns out to have some form. But then, if you compute the actual shape of that two-point function in terms of the time difference between these physical operators, you actually find that indeed in the Q to 1 limit, which is the limit where G Newton goes to 0, that this two-point function indeed matches with the bulk-to-bulk two-point function in de Sitter space, in 3-dimensional de Sitter space. So there are indeed operators in this theory that represent basically operators that live on the world line of some observer in this space. So that this expression, I found it in papers in Zurich. Yeah.
So the bulk-to-bulk of which operators? Wilson lines or?
Of local operators, of free field operators of particles of mass m. So in the same way as that in ADS-CFT, if I have an operator with a given mass, it corresponds to a certain local operator, at least the field operator of bulk particle is a local operator in the CFT on the boundary. In this case, the field operator, or the operator in the quantum mechanics, is an operator that creates a particle here, and I'll have a slide on the next one, and it does this. But you're right, this is a world line, so it's a two-point function. So from the point of view of the 3D theory, this is a line operator. But from the point of view of the just doing the G Newton to 0 limit, I'm just doing actually quantum field theory in this space, and this does have to be a two-point function. More recently, we actually understood why this thing works. Because I had a magical formula where I was doing this thing here on the boundary, where I basically made this convolution product basically of 2 operators. Turns out that the mathematical reason for why this thing works is that in the Sitter space, I explained that the boundary sits here. I reproduced the bulk-to-bulk two-point function as a two-point function of two of these objects. If you decompose basically that two-point function accordingly, basically it's a version of Herman's theorem or Green's theorem, where basically I'm writing down this Green's function as a convolution product of one bulk to boundary Green's function times the boundary to bulk Green's function. So that's why this thing actually works. So this is one piece of evidence. Are there questions about this?
I have a question. What would it be the Liouville picture of this correlator?
Yeah, I have a paper with a student where actually the same correlator, it's a slightly confusing question, but basically where it's being reproduced by a boundary to boundary two-point function. So indeed, if you take the boundary to boundary two-point function in this complex variable theory, it reproduces this.
What it would happen with the three-point function? Because the three-point function I expect in the SYK to be 0, but in the Liouville side is not 0.
Yeah, we should talk about this. Actually, yeah. In some sense, this is the three-point, because basically you kind of do it like that. Because there's a label here, a label there, and a label here. So
It's a spherical three-point function. But I'm talking about the disk three-point function, boundary, boundary, boundary.
yeah, I haven't studied, but that's good. So this was the Green's function story. Here's the. Okay, let me very quickly mention indeed now sort of a development which puts this, I think, on much more rigorous footing, where one can actually completely reconstruct the full algebraic treatment of the SYK model, starting from the SL2C Chern-Simons theory. And you can even relate it, as I mentioned, to this supersymmetric gauge theory. So that there's technology that people have developed to do exact computations in gauge theory, Chern-Simons theory, and DSSYK, and the things match. And I can tell you what the dictionary is, and it's kind of interesting. The idea is the following, is that suppose that I live on the North Pole and I actually put some matter also on where I am, so I contribute some matter to that theory, so I create this conical deficit. And the basic idea that I started to explore at some point a year ago was that what I call the SYK Hamiltonian, if you recall, its eigenvalue is the cosine of an angle. So I thought, hey, maybe this thing is actually the loop operator that measures the conical deficit here. Since we talked about the holonomies, so here's what I'm going to do. I'm going to write down the quantum operator that measures that holonomy. I'm going to write down my phase space, and I'm going to compute the spectrum of that holonomy in the gravity theory or in the gauge theory. And it turns out that that problem mathematically maps to the problem of this ground state of disputed quantum monopoly. The two things are the same. So the idea is the following, is that I have a sphere. This is half the sphere because this is basically the North Pole and this is the equator. And then there's another side to the universe that sort of completes the sphere. And I have one variable which goes around the equator, which is the holonomy that goes around the equator. And I'm going to have a canonically dual variable, that's the Wilson line, or at least the holonomy that goes between the North Pole and the South. So I have a North-South Pole operator, and I have a thing that goes around the equator. Okay. Now, since these things are part of a quantum theory, I should expect that those two operators don't commute. And so the first thing I need to do is to actually compute their commutator. So here's another picture. So this is the zeta space. This sphere is actually a spatial slice in the zeta space. I have an operator that goes around the equator and an operator that goes between the North and the South Pole. It turns out that actually, since this is essentially a version of hyperbolic geometry, I can actually initially also compute classical relationships between these holonomies. And it turns out that those classical relationships go back to an ancient guy, Ptolemy. So there's a thing called Ptolemy's theorem, which is basically a clever version of Pythagoras. I talked about the operators that go around from the North Pole to the South Pole. I talked about operators that go around the equator. There are also operators that actually go around the punctures at the North and the South Pole. And there are operators that go between the North and the South Pole, but that also wind once around the equator. So imagine that you travel from the South to the North Pole while also going once around. And all those operators will have intersection points, so later on we're going to find that they actually don't commute. But they also have relationships, and those relationships turn out to be a version of Pythagoras. Basically, this guy told you that if you have any quadrilateral, how do you call that? A thing with four sides. Quadrilateral. And you take the product of two diagonals. It's equal to the sum of the product of the two things that sit on the north and the south times the thing that sits on the only version that I actually can prove myself here easily is for a square. Let's go ahead 2 squared is equal to 1 plus 1. But it's not too hard to do this thing more generally. And it turns out that these holonomies actually satisfy the same relation. And then it turns out that those relationships at least have a certain form. Maybe I'm going to skip in these since I don't have too much time. That there's a certain classical relationship that one can write down. So Z is going to be the thing that goes between the North and the South Pole. Y is the thing that goes between the North and the South Pole while circling once. Y tilde is the thing that circles the other way around. And L is the thing that goes around the equator. Okay, so these are classical relations. But now I'm going to insert some Q's in this relation. Q is the thing that has the level of the Chern-Simons theory in there. And the reason why the Q's come in there is because of a famous relation which sort of drives the whole development of the not polynomial.
I suppose this can be derived from the isometries of the system. So it's like the Lorentz contraction, but for the...
Yeah, it's some group theory, and it actually occurred in earlier papers by Penner as well. At least people have studied this. But anyway, in Chern-Simons theory, you have that particular commutator up there. Turns out that if you look at the Wilson lines in Chern-Simons theory, they satisfy something that's called a skein relation. Depending on the ordering of the Wilson lines, you pick up a Q here or a Q there. So this crossed Wilson line can be decomposed into two non-crossed Wilson lines like that, with factors of Q in front of it. And it turns out that if you now put those factors in Q in there, then you get the following equation that if I multiply this thing by that, I can decompose it like that. And this is, here you can see the skein relation, that this crossing can be uncrossed like that. So this is actually a relation in the Chern-Simons theory. And a long story short, that there's a simple generalization where you also can derive this particular commutation relation between the Z variable and the Y variables. This turns out to be equivalent to the Q-deformed harmonic oscillator system. So there's a dictionary where indeed the two things are matched. So this was an insight that came sort of roughly a little bit more than half a year ago. Then I wrote my paper, and then Vili Viotto sent me a short email saying, hey, do you want to come give a talk at Perimeter? I gave a talk at Perimeter, and he says, well, all your formulas look like sure indices of four-dimensional gauge theory. So if I have 2 more minutes, I'll tell you a little bit about the connection with four-dimensional gauge theory. But basically this kind of sort of makes this connection already pretty strong. But now there's this fourth corner, which is the four-dimensional gauge theory, and which is kind of a cute one. So here's the idea, is that, so Sarbeck and Witten cleverly solved n equals 2 Yang-Mills theory. They started indeed with SU2, and they basically studied what's called the Coulomb branch, where you give an expectation value to the Higgs field. And you study how the various charged objects in that theory depend on the expectation value of the Higgs fields. And there's some rigid type of geometry associated with that, and that geometry can be captured by introducing something that we now call the SYK curve. The SYK curve is a two-dimensional curve that is parameterized by the expectation value of the Higgs fields, and it also has information about the gauge coupling because of the beta function. The gauge coupling depends on the Higgs field, the value of the Higgs field. 10-15 years later, AGT came around where they sort of put this on a different geometrical footing, where they sort of explained a relationship indeed of the Nekrasov partition function, which kind of proved the written solution, the SYK solution, in terms of a Liouville theory on a two-dimensional surface. The Liouville theory on a two-dimensional the two-dimensional surface associated with SYK theory looks like a sphere with two punctures. So this particular surface here, indeed, is the curve on which you have to compactify the six-dimensional 2,0 theory to get the SYK theory. Now, the following claim is then true, is that in the SYK theory you can indeed start computing nice quantities which turn out to be supersymmetric indices, and you can introduce operators that are also supersymmetric BPS operators that are inserted in those indices. And the operators that you can include in the gauge theory are the Wilson lines and the dionic Wilson lines, basically the 't Hooft lines. Now the beauty of the AGT correspondence is the following, is that, let me briefly do this for n equals 4 YAMLs. For n equals 4 YAMLs, the curve on which you have to compactify the gauge theory is just a torus. And the tau parameter of the torus is the Young-Mills coupling, 1 over the Young-Mills coupling. And it's pretty clear in that case that if I would have an object that goes around the A cycle, so it turns out that if you have the Wilson line of the Chern-Simons theory defined on this space, but where this would be, say, a torus, then the A cycle thing would be the Wilson line, the electric charge object, and the B cycle thing would be the magnetic charge object. Same thing is true here. The Wilson line of the SU2 gauge theory turns out to be the Chern-Simons Wilson line around the A cycle. And all these funny Wilson lines that go between the North and the South Pole, they correspond to the 't Hooft Wilson lines. Now it turns out that the 't Hooft lines in the 4D gauge theories and the Wilson lines of the gauge theories satisfy an algebra. And that algebra matches with this thing that I call the Skene rule of this tables. So indeed there's a dictionary between what you can do in a 4D gauge theory and in the Chern-Simons theory. And in a funny way, it turns out that actually the gauge theory is the easiest way for computing, even easiest method for computing quantities. And the reason is that the quantities that you're actually computing don't depend on the gauge couplings. And it turns out that that particular thing that would be the partition function, which is the index, can just be computed in the free field theory limit of the gauge theory. And indeed, when you do that, the answers that you're going to find indeed match with the correlation function of the SYK one. So I'm not sure if in the end I've convinced you that SYK has something to do with the sitter, but I've given you, you can maybe call it circumstantial evidence. But I think my lesson is the following, is that by trying to see how the two things match, and I know that I'm actually talking about a quantum system, I'm certainly learning something about the sitter holography. And I sort of have a guiding principle, at least for maybe deciding which choices to make, even though a priori it might not really seem natural. But basically the quantum system itself might guide us in the right direction.
I have a question about the HGT. Right? So at least in its original version, HGT is for super conformal. So in that case, you need, in order to be in the conformal window, the cyber witness has to be supplemented with 4 flavors.
Correct.
And in that case, if I remember well, the 4 flavor is not in a sphere with 2 punches, it's a sphere with 4 punches.
That's right.
So how it matches?
So this is pure cyber-witness theory.
But it's not super conformal.
So it's not super conformal, so the 2 punches are actually called irregular punches.
These irregular operators in unity.
So it's just the irregular operator. And this is precisely where the structure matters.
Yeah, we had a lot of questions during the talk.
Yeah.
Yeah, anyone who wants to stick around. Oh, yeah.
Yeah, maybe give me half a minute
I
though
was-
to give one. Yeah, go ahead.
No, yeah, I mean, this is, I mean, I don't know the double scaling, but I mean, you wrote the Hamiltonian of SYK in double scaling as a summation of A dagger and A, okay? But in the end, I mean, in SYK, in the original one, you have a system of fermions, so you would
Correct.
say that you would have, you can have only one fermion on each side, however, we have a tower of states here.
Correct.
So the way you are defining the states in this
Correct.
change of basis versus what I imagine they have fermion or no
Correct.
fermion, what's sort of the transformation of a Wally
Yeah,
something
very,
to be
very good question, and it's related to actually a comment I wanted to make. In order to go from the actual microscopic SYK, where you can actually see all the different states, to this very restricted set of operators that I introduced, the A and the A daggers, I made a pretty big projection. Basically, so nowadays people like to talk about von Neumann algebras, and at least in the context of CFT a little bit, so you talk about operator algebra. So let me give you the slightly more abstract language here. So you have this big system, SYK. It's called actually, so von Neumann obviously was brilliant. But anyway, he had a thing he calls type 1. So what is type 1 is the thing that you and I would call a system with actually a finite number of these. If you don't know what the Hilbert space is, I just count and I actually do quantum mechanics. So that's type 1. Type 2 is a slightly funny beast. The way I'm thinking about it essentially is you do some funny double scaling limit. And you only keep certain operators in your spectrum that survive that limit. And then you define a set of an operator algebra, which is not capable of making all the distinctions of the large N system. Call that the A and A dagger algebra, or slightly more generally. And that operator algebra is then turned out to be type 2. So type 2 algebras in von Neumann classification are a little bit of this type. They kind of secretly know that they're part of a much bigger system. And it turns out that in type 2 algebras you can never measure this number. So type 2 algebras have an entropy, a von Neumann entropy, that you can associate with it. Because you can say, hey, what's the density matrix that my algebra can see? And I can compute relative entropies in that system. Differences in entropies. But I cannot compute the overall constant. So what's going on here is that we're taking a limit where we have some kind of soluble subsystem, but that subsystem lives in a bigger algebra. But by von Jones, who kind of preceded the discussion of Chern-Simons, the way he discovered the Jones polynomial was to study type 2 algebras. He studied things he called subfactors. So basically, in this case, you can have inclusions of algebras. But anyway, in the end, you only focus on this. Okay? Let me try to give one last sort of more physical answer to how I'm interpreting this thing here. It turns out that the SYK model in the Q to 1 limit has actually isometry generators that you can write down that allow you to take operators and to move them all around the city space globally. So the way I find that surprising to some extent, because often when we talk about holography, we would say, hey, I have an observer, I have a static patch, and I want to explain my observations in the static patch, and the static patch has a certain entropy associated with it, with this horizon. But if I look at the future infinity of the city space, the static patch actually is actually of this drawing here. Slides, I think. this is the static patch. If I go all the way to future infinity, that static patch becomes a point in infinity. It's just a tiny region of the total future infinity. So in the end, if I want to be able to have a quantum system that can describe this whole global space, I probably need a Hilbert space that's much bigger than the Hilbert space that I'm associated with one of these patches. So my interpretation is that what this entropy is doing, it's sitting there basically as a way of being probed once you get to know more about the microphysical theory. And you have to start making many copies of that algebra to fill up the whole system. So that's currently my idea, that this should actually be thought of more as a model maybe of inflation, where you actually not only have one patch, but you have many patches.
You say there's some unitary or something in SYK in this limit that corresponds to moving this.
Right, yeah, actually one of the subtleties is precisely whether or not it's
Whether it's
unitary.
unitary, yeah.